In this video clip, I'm going to go over the answer to question 1 in video exercise 1. So this was taken from an exam a few years back. Like for like, apart from that I added part E to go in line with lecture 2 in deriving the covariance and autocovariance autocorrelation function of an ARMA 1-1. So in the lecture handout, it showed how we can back recurse the ARMA 1-1 by substituting in yt minus 1 and then yt minus 2 and going back and back and back. And we can see that under a certain under the assumption the AR1 coefficient in the ARMA 1-1 model is less than 1 in absolute value, we saw we could write it as its MA infinity representation, very similar to the case we did for the AR1. Okay. So this question is related to that. We're going to derive the MA infinity form of an ARMA 1-1 and then use that to then derive the mean, the variance and the covariance and correlation function of a ARMA 1-1. Okay. So to do this, it uses a slightly different method to the one we've seen in the lecture notes. Okay, but it does the exact same thing. So what this question says is, this gives all the information on the question here. It says, suppose we have an MA infinity representation, any, for some coefficients e to s, such that they satisfy conditions 1, 2, and 3. Okay. So what does it say that they satisfy? Well, as always, we normalize e to 0 to be 1, condition 2. Condition 3 says that e to 1, the first coefficient, is just some phi 1 plus e to 1. And then number 1 says that these MA infinity coefficients e to s satisfy this different equation here, for s is greater than or equal to 2. And again, this just says that condition 1 just says that e to 2, s equals 2, we're going to get e to 2 equals phi 1 e to 1. Then going again at e to 3, we're going to get phi 1 e to 2, etc. For any s, any s greater than or equal to 2. Okay? So it just says we've got some MA infinity process and the coefficients in the MA process satisfy conditions 1, 2 and 3. Okay, this just reiterates what I said above here. The question part A then asks you to show that this turns out to be the MA infinity representation of an ARMA 1-1. Namely, that the MA infinity representation of the ARMA 1-1 would have MA infinity coefficients, call them eta, which satisfy conditions 1, 2 and 3. Okay? And to show that then, what we're going to show is, well, the question asks you to show that yt minus phi yt minus 1 equaled mu plus epsilon t plus phi 1 epsilon t minus 1. Okay, so this is what we're going to show now. And we can see that once we can show this, we can just rearrange, and this is just the taking the yt minus 1 to the other side. This is just by definition the ARMA 1-1 process. Okay, we have an ARMA 1-1. Okay, so we can just use then all the information given here to then derive what this is here, yt minus phi 1 yt minus 1. Well, firstly, use this equation here to write yt, just expanding out. Okay, we're just going to get alpha plus the s equals 0. We're going to get e to 0 times epsilon t. Then s equals 1. We're going to get e to 1 epsilon t minus 1. And keep going and expand out the sum, and we can keep going forever and ever and ever. Okay. Do the exact same thing for yt minus 1. Now, using this equation again, it holds for any time period, lagging back one period. We can now expand out yt minus 1. It's equal to alpha plus s equals 0. We're going to get e to 0, which is 1, times by epsilon t minus 1. And again, just write that here so we can see the like-for-like shocks. Okay, so we're writing them so we can see as we go down, we're picking out the common shocks. And again, at s equals 1, we're going to get e to 1 times epsilon t minus 2. And again, we're going to get this. And go along as... Okay, so we've just expanded out yt and yt minus 1 using this equation above, okay, which has been given to us. Okay. We now then, the question then asks us to work out what yt minus psi1 yt minus 1 is. So we just subtract psi1 yt minus 1 from yt. Okay, so we can just multiply, we'll just now multiply both sides by psi1. We're going to get psi1, etc. Dot, dot, dot. And just subtract one from the other. And this is what we do down here. Okay, so we can see then, subtracting, we're going to get, well, we're going to get alpha minus psi1 alpha, we're going to get part A, plus epsilon t, there is no epsilon t in this part here, plus, then we're going to get e to 1 minus psi1, e to minus 1, here, subtracting this from this. Then we're going to subtract this, we're going to get e to 2 minus psi1, e to 1 of epsilon t minus 1. Then we're going to get this minus the other one. So we're going to get e to 3 minus psi1 e to 2. And you're going to keep going on dot, dot, dot forever and ever and ever. Okay. Let's get rid of this. Okay. So then, let's put that back in the box. We can now simplify then. Well, part A, just define mu as alpha 1 minus psi1, gives us part A. Then, we're just going to get plus epsilon t. Then, what we're going to get for part B, well, we know that from part 3, that e to 1 is the psi1 plus d to 1. So we can just substitute this in to get theta 1, epsilon t minus 1. And then finally then part C, all the remaining terms are equal to 0 because they all have this form, i.e. e to 2 minus psi1 e to 1 is 0, and the same for e to 3 minus psi1 e to 2, etc. Because we know for any s this equals 0. We're told this in the question. So we've used 1, 2 and 3 to show that an MA infinity coefficient, an MA infinity process with coefficients satisfying 1, 2 and 3 is an ARMA 1, process. Okay, that's what question A asks you to do. Okay, so now moving on. Okay, so this just reestablishes then, we've just found that an MA infinity representation, an MA infinity process with coefficient satisfying 1, 2 and 3 is the ARMA 1, process. Okay, so we now have the MA infinity form of the ARMA 1. We've got e to 0, it's 1. We're told what e to 1 is. We now need to solve for the remaining e to s. Well, e to s for s is greater than or equal to 2 is just a first order difference equation. So the next part then is just going to solve for e to s. Well, using the definition, e to s is psi1, e to s minus 1. Then substitute in, recursing back, we can substitute in, going back, e to s minus 1 is psi1, e to s minus 2. Plugging that in, we're going to get to here. Then again, we're going to get to here. And we can see a pattern occurring then. Okay, we can see that the power matches the lag. And again, so we've gone back once here, we've got psi1 squared e to s minus 2. We've gone back twice here, and we've got psi1 cubed e to s minus 3. And if we go back at a general, just s minus 2 times, we can see then the power is now going to be s minus 1, and we're going to get now e to the 1. We've gone back s minus 2 times, so we're going to be left now with this here. Okay. So we've just solved a first order difference equation where we know then, by the question, we're told that e to 1, which is just the initial condition. Okay, so we can plug this in and we've done then. We've just solved a simple first order difference equation to find the exact form of the MA infinity coefficient of the ARMA 1. Well, they look like this here. Okay. And we can see then that this also holds for s equals 1 as well, because we know that eta 1 looks like this, which can just be expressed as phi1 to the naught times by this, because remember, anything to the power naught just equals 1. So actually this condition holds for all s greater than or equal to 1. So now we've got everything. Okay, we have eta naught equals 1, and then we have that eta s equals phi1 s to the minus 1, phi1 plus theta 1. For the rest, for all s is greater than or equal to 1. So if you look in the lecture notes, this is exactly then the MA infinity representation which we derive for the ARMA 1-1 model. We've just done it in a slightly different way. We've seen that the ARMA 1-1 coefficients satisfy this difference equation, so they're both doing the exact same thing. Okay, we could have got here just by back substituting again and again and again, as we did in the lecture. Okay. So part C then asks you to verify the absolute summability condition, which is just this here. It says, it's just a definition, it says that the sum of the absolute value of all the MA infinity coefficients are less than infinity. Okay? And remember why we did this. Remember that for an MA infinity process, in general, the variance is sigma, looks like this. It's the sum of all the coefficients squared. And remember, for it to be stationary, this has to be finite. And we saw, we don't need to prove this, but we know the result that absolute summability implies what's called squared summability. So when we're doing this, the reason why is we're just showing the conditions when the ARMA 1-1 will be stationary. Okay? We've expressed the ARMA 1-1 in its MA infinity form, i.e. we have all of the MA infinity coefficients for the ARMA 1-1 representation. Okay? And we now want to see, well, under what conditions on these coefficients is it stationary? Well, we need to verify the squared summability condition such that this variance is finite. And again, because the absolute summability implies squared summability, then this will also give us a condition. Okay, so we're now just going to see under what conditions on the model parameters will this hold. Well, just use a definition. Okay, we can break up the sum. Okay, so we're going to get s equals naught, which would give us, remember, eta naught is 1. Then plus the remaining part of the sum from s equals 1 to infinity. Okay, so we break up the sum. Then we now want to substitute in for eta s. Well, we know that from above, eta s equals this. For all s is greater than or equal to 1. We just found this above. So we're literally just plugging this in to here. Okay. Then we can use the result that the absolute value of two numbers times together is just equal to the absolute value of both times together. To break this up again. And then we can just take this number outside of the sum. It's not, again, this is not a function of s, which would get us down to here. Okay. Then all we've done now is we've just shifted back one period. Okay, so these two things are equal to each other. Okay, and to see that, well, we can see that writing this out, sigma s equals 1 to infinity. So again, if you're not sure these things, just write them out longerhand and see what happens. So we're going to get the sum from s equals 1 to infinity. So s equals 1, we're going to get phi 1 to the power naught, which is just 1. Then s equals 2, we're going to get the absolute value to the power 1. Then we're going to get plus phi 1 squared, dot, dot, dot. And we can see this is just exactly equal to this here, shifting back one period. Again, at s equals 0, we get 1. We're going to get, at s equals 1, we're going to get the absolute value to the power 1, etc. We're going to get s equals 2 phi 1 squared. The two things are equal to each other. Okay, so we just shifted back one period to get from here to here. Well, what's this? This is just a geometric progression in phi 1s. Okay, we just have 1 plus absolute value again, just as we've shown before. This part here is 1 plus phi 1 plus phi 2 squared plus dot dot dot. So again, if the absolute value of this is less than 1, we know that this is 1 over 1 minus phi 1. Okay? And then this whole thing is finite then. So we can see that if the absolute value of phi 1 is less than 1, that the sum is finite. And we can see that, take the case for example if phi 1 equals 1, this sum here is obviously going to explode to infinity. If phi 1 just equals 1, we're going to get 1 plus 1 plus 1 plus 1, an infinite number of times, and it's going to be infinite, and the same thing if it's greater than 1. So we can see that if phi 1 isn't less than 1, this is going to diverge, and therefore it will not be absolutely summable. So we've just shown then that we derived the MA infinity form of the ARMA 1-1. We found the coefficient, e to s, here. We solved here for all the coefficients. Exactly the same form as we derived in lecture by back substituting. We've now shown that under the condition phi 1 is less than 1, that the variance of the MA satisfies the absolute summability condition, which just means that the variance is finite, which so therefore it's stationary. So then we found that the ARMA 1-1 is stationary when this phi 1 coefficient is less than 1 in absolute value, which is exactly the same condition as we needed for the AR1. Okay? And intuitively, we need this phi 1 to be less than 1, otherwise the effect of the pass will never die away. If phi 1 was greater than 1, the series would be explosive, exactly as the case for the AR1. Okay, so part A, we showed that the ARMA 1-1 was a particular MA infinity where the coefficient satisfied some restriction. We then solved for these coefficients here. We got the ARMA 1-1 form, which we could have done equivalently by back substituting as we did in the lecture notes. And we've then shown that for this MA infinity process, which remember is exactly just the ARMA 1-1 re-expressed, we showed that if this restriction held on phi 1, that the process is stationary. So we've derived the MA infinity form and given the condition for stationarity, which is part A to C. Okay. So we're now then going to derive the variance. Okay. For a stationary AR1. So again, the first part here, this is just the general formula for the variance of an MA infinity. Okay. And remember, we have all these e to s, we derived them a second back. Okay. Again, we can break up the sum into two parts. Okay. We're going to get s equals 0, we're going to get e to 0, which is 1. And then we're going to get plus the rest of the sum. Okay. Then what do we get then? Well, we can just substitute in the coefficient for e to s, which we know we derived earlier with this form here. So again, we'll just substitute in, and we're going to square it. So hence why we can take the theta 1 plus phi 1 squared outside. Then we're going to get this thing squared here. So we're going to get, this is why we get the 2 here. So we're going to square this, plug it in. Again, we can re-express the sum, lagging it back one period. Okay, just as we did before. And remember, to show this, again, if it's not clear by looking, then we can see, writing out longhand, sigma s equals 1 to infinity of phi 1 to the 2 s minus 1. Well, at s equals 1, we're going to get phi 1 to the 0, which is 1. At s equals 2, we're going to get phi 1 to the 2 times 1, which is going to be phi 1 to the 2. Plus, at s equals 2, we're going to get phi 1, 2. Sorry, at s equals 3, we're going to get phi 1 to the power 2 times 2, which is 4. And so on. Which is just the same as this formula here, which is like back one, which is just this. Again, phi 1 to the 2s. S equals 0, we're going to get phi 1 to the 0, which is 1. Plus, s equals 1, we're going to get phi 1 squared, phi 1 to the 4. So the two things are equal to each other. So again, we've just gone back, we've re-expressed the sum by lagging it back one period. And again, this is just a geometric progression in phi 1 squared. And again, because we've assumed phi 1 is less than 1, it implies phi 1 squared is also less than 1. Okay, then we're done. The next part then just multiplies and divides 1 by 1 minus phi 1 squared, and just then re-expresses the numerator and denominator in this equivalent form. So the left part then is just simple algebra. Okay. So this is then the variance of this particular MA infinity process, which again we've shown is equivalent to the ARMA 1-1. Therefore, this is the variance of an ARMA 1-1 process. Okay. So part E then, we can now go on and, but in a similar vein, we can derive the variance, autocovariance function and the autocorrelation function. And again, the question didn't give you this, but you could have taken it from your notes. Remember the general formula for the covariance function of MA infinity is this. Okay, and remember we've derived, we know what these e to s are. We know that e to naught equals 1, and that e to s equals phi 1 plus e to 1 times phi 1 to the s minus 1 for all the rest of the s. Okay, so these are all, we solved for these earlier on, we've been using these again and again. So we first off start with k equals 1. Okay, this is just the covariance at lag 1. Again, using the formula at k equals 1, we get to here, putting k equals 1, general formula. Breaking up the sum again, we're going to get this here. Okay, so at the s equals 0, then we're going to get e to 0, e to 1, which just equals e to 1, because e to 0 equals 1. Okay, so we've broken up the sum. Then what we're going to get, well, we know that e to 1 equals phi 1 plus d to 1, just from here. Okay, and then we can now plug in, as we've done before, e to s, for s is greater than or equal to 1. Okay, so we're going to get this thing squared, so now we need to work out, well, what's e to s plus 1? So just to be clear, we're going from here now down to here. Well, just plug it in. We're going to get phi1 plus phi 1 squared. We're going to get phi to 1 s minus 1. And we're going to get phi to 1 at s plus 1, so it's going to be s. Okay? We're going to get e to s, and then e to s valued at s plus 1 is going to give us s. Okay? So we're going to get phi to 1 plus phi 1 squared. We're going to get now phi1 2s minus 1. Okay? So we just plug that in to here and take this outside, the squared part, because it's not a function of s. Again, we can re-express, and again noting that we can rewrite phi 1 for 2s minus 1 as this. Okay, because look, this here on the right hand side is 2s times phi 1. Again, we just add the powers together, so we're going to get 2s minus 1 plus 1, which is just equal to phi 1 to s minus 1. When we expand that, we're going to get 2s minus 2 plus 1, we're going to get 2s minus 1. Okay, then we can plug this in. Okay, obviously the phi 1 is going to come outside. Okay, and then we've also lagged it back one period. We've re-expressed the sum. Okay, as we've done before. So again, using the methods, using the ideas from before, we can rewrite all of this equivalently as this here. Okay, and then we're done. Then, well, what's this? This is just again a geometric progression in phi 1 squared. Okay, hence we can then solve. So we can, again, this is just going to be 1 over 1 minus phi 1 squared, which gets it down to here. Okay, and again, because we've assumed that phi 1 is less than 1, and then we're done then. We can just then take the theta 1, again, we can take this outside, and we have then the covariance at lag 1. Okay, which is what was seen in the question. Okay, we can now do it then for lag 2, and all remaining lag. Okay, so now we can see that we can now solve for the remaining autocovariances for all k greater than or equal to 2. Well, first off, we have, remember, general formula for any k, and just now we're going to do it for k greater than or equal to 2. We can then break up the sum again. We're going to get, well, at s equals 0, we're going to get e to k, then this is going to be the rest for s equals 1 and onwards. Well, what's e to k? Remember, e to k is just going to be, we're just again plugging in the formula for e to s, which we've been doing repeatedly now. Remember, e to k is equal to phi 1 k minus 1 of phi 1 plus e to 1. Okay, plugging that in, and again also plug in, well, what's e to s plus k? Well, e to s plus k, just using the formula, is going to be, well, we're just going to get phi 1 to the s plus k minus 1 of phi 1 plus theta 1. And we're going to get this thing squared. So again, this is why we're going to get this. We could take the phi 1 plus theta 1 squared outside, and we're going to get this to the power 2, which is why we get this here. Okay, so we'll just square this and plug in, so we can get down from here to here. All we're doing is using this formula and plugging in the coefficient into here. Okay, and again, we can now re-express phi 1, this here, in this equivalent form, because the powers have to add up together. Okay, such that we can take then the phi k minus 1 outside to here. Okay, as we did before, we can re-express the sum going back one period. We can show if we write these two things out longhand, they're equal to each other. Okay, and then we can see then the phi k minus 1 is appearing here, so we can take it outside, and the remaining term in the brackets we just saw above is the autocovariance at flag 1. Okay, so what we've shown is then, we've shown all parts of the question now. So we've shown that the covariance function looks like this. We derived it for k equals 1 above, and then we showed then for all remaining k greater than or equal to 2, it takes this form here. So this then here is the autocovariance function of an ARMA 1-1 process. Okay, once we have the autocovariance function, then we can always derive the autocorrelation function just using the formula. It's just the autocovariance divided by the variance. Gamma naught is just the variance. And we derived the variance earlier, it's this term here. So to get row 1, it's just going to be gamma 1 divided by gamma naught. We have gamma 1 here, we've already derived it. So we're just using now the formula. So we can now, once we get to this part, it's relatively straightforward. We have the formula for gamma 1, we have the formula for gamma naught, we can then just divide one by the other. Okay? So we're just multiplying top and bottom by 1 minus phi 1 squared. Okay? Then going down then, well, we can just simplify then. Well, we can see then we're going to get phi 1 squared cancelling out, which is going to simplify down to here. Okay, so we've derived then the first correlation, just using simple algebra. Then for the rest then, well, for k is greater than or equal to 2, we know that gamma k takes this form here. So we could just use this formula, divide by gamma naught, and we're going to get this here, because this by definition is just row 1, which is derived, and again we get this recursive form for the correlation function of an ARMA 1-1. Okay? So once we have the variance and the covariance function, it's straightforward then to derive the correlation function. And we can see then, well, that we can make some comments on this, because what happens, well, we can see that if phi 1 equals 0, well, for an ARMA 1-1, if phi 1 equals 0, we just collapse down to the AR1. Remember the formula for the AR1. So if phi 1 equals 0, it's just equal to mu plus phi 1 y2 minus 1 plus epsilon 2 if phi 1 equals 0. Okay? So in this case, at phi 1 equals 0, we should find that the correlation function of the ARMA 1-1 at phi 1 equals 0 collapses to that of an AR1, and we can see that this happens. We can see that in this case row 1 equals, well, if phi 1 equals 0, we're just going to get theta 1 divided by we're just going to get theta 1. Okay? Then we're going to get theta k for the rest of the k greater than or equal to 2 is going to be, well, it's going to be phi k minus 1 times by phi 1, which is phi, which is just equal to phi 1 to the k. So in that case then, the whole correlation function just equals rho 1 to the k, which we saw for the AR1. Okay? So we can see then that everything fits together then. The main difference between the ARMA 1-1 and the AR1 is the addition of this shock, epsilon t minus 1. And this is why the correlation function looks exactly the same for k is greater than or equal to 2, relative to the AR1, it has this recursive form. It's going to decline exponentially quickly as k increases. But now the correlation at lag 1 can take basically any number between 1 and minus 1 as we vary the coefficients theta 1. Okay, because this addition of this shock allows the correlation at lag 1 now to vary relative to the AR1, where we couldn't do this. So that's kind of the intuition of why the correlation function looks the same. It's just now it's more flexible in that this process allows a more general pattern of correlation at lag 1, which you'd expect because theta 1 will govern, will explain, theta 1 governs how the shock affects yt, and therefore as theta 1 gets bigger and bigger, it means the shock is affecting, from last period affects yt more. We'd expect a stronger correlation with yt relative to what we'd expect in the AR1, which obviously doesn't allow this. Okay? So just to recap then, we derived the MA infinity of the ARMA 11 using this difference method. Again, if you want, you can just, we can look at the notes. We can also do the exact same thing by back recursing. We then use the general formulas for the variance and covariance of an MA infinity to derive stationarity, to derive the condition for stationarity, and also to derive the formulas for the variance and the covariance, and then the two things together to get the correlation function. Okay. The final part then asks you to comment on, well, what happens in the AR1 if theta 1 equals minus phi 1? Well, we can see from the formulas, this is a formula for the correlation at lag 1, well, this just equals 0 in this case, so we're going to get 0. And again, when rho 1 equals 0, then all the rest of the correlations equal 0. This just means then, if theta 1 equals minus phi 1, the process is uncorrelated at all lags. Okay? So you can see that just by plugging in this restriction into the formula, which is all that you had to do. But why is this the case? Well, what happens under this restriction? Okay, well, under this restriction, remember, so the ARMA 11 simplifies, enforcing the restriction. Okay, then we can just simplify down. Okay, because phi 1 is the coefficient on both, so it's simplified down to here. Okay, then we can back substitute again. This holds for yt, it also holds for yt minus 1, go back one period, and substitute into here. We're going to get down to here. And if we keep going then, j periods back, we can see we're going to get this sequence developing as normal. And we're going to get phi 1 to the j plus 1 times by this term here. Okay, and as j goes off to infinity, this tends towards 0. So we can see then, as we can see when phi 1 is less than 1, the ARMA 11, where the theta 1 equals minus phi 1, is just equal to a constant plus a white noise shock. Hence why we found that when this restriction holds, when theta 1 equals minus phi 1, we find that the ARMA 11 will be uncorrelated at all lags. Okay, and the intuition is, again, is that if this holds, then the shocks are kind of balancing out. We can see here, if, when we have yt in the general ARMA, we have this here, plus theta 1 epsilon 2 minus 1. Okay, so if the theta 1 equals minus phi 1, as we saw before, it's simplified, we're going to get now, the effect of the shock, it's subtracted out. So again, the effect of the shock from last period is having no effect now. So it's taking out all of the correlation in the series, and this is why we find that there's no dependence with past lag. And we saw this formally by back recursing. And you can see this back recursing method is very common. Okay, so you have to be very comfortable with this back recursing model in relatively simple models. Okay, for example, you wouldn't be expected to do it in, say, an AR4 or 5 or something which is going to be very, very complicated. But in the AR1 or the ARMA 11, okay, it's very simple because we just have to recurse the one variable yt minus 1. Okay, so that's the end of it.